Okay, hello everyone, and welcome to week 7 lecture. And today's topic is going to be the rigid body dynamics and emotion analysis. I know that you may actually cover some of these topics earlier, but once again, we're going to have a revision for that, and we're going to have some examples on how to do the analysis and how we're going to use the SolidWorks to do this analysis, and how to use the MATLAB with the Simulink to do the rigid body dynamics and motion analysis. So today topics is going to be, or contents of this lecture is going to be the introduction, the rigid body dynamics, the fundamentals of the rigid body dynamics, the dynamics analysis, and the application of the RPD. Then we're going to talk about the motion analysis using the SolidWorks and the motion analysis using the MATLAB, Simulink, and the Simscape, which is going to be part of your project basis that you're going to use to do the analysis for the bodies that we're going to assigned to you. Just remind you about the tutorial and computer lab on the week 7, 8, and 9. We're going to have the week 7 starting from the 15th of April, which is going to be the Tuesday, I think. We're going to have tutorial about the fundamentals of the MATLAB, Simulink, and Simscape, and the motion analysis. The computer lab is going to be followed on the next day to have the 4-bar linkage and the piston slider. That's something that the student who are doing the mechanical design also going to have it. The week number 9, starting from 22nd of the April, Tuesday, we're going to have tutorial first about the fundamental of the MATLAB, Simulink, and the Simscape, and we're going to do the single degree of freedom mass spring damper system, and then we're going to have the computer lab next day about the single degree of freedom carved road surface analysis. The week 10, starting from the 29th of April, Tuesday, we're going to have a tutorial about the fundamental of the MATLAB, Simulink, and Simscape. We're going to talk now about the multiple degree of freedom mass spring damper system. And the next day, we're going to have a computer lab about the multiple degree of freedom race car with the two wishbone suspension analysis. So let's start with the introduction first. So in the introduction, first we need to understand what is the rigid body dynamics. Now, every machine is going to have some moving parts, or sometimes going to be no moving parts. But anyway, most of these parts are going to have a motion, which is a dynamic base, that either going to be horizontal or radial or both, like what we have in the case of this crane. When we're going to have, sorry, let me get the pointer. So when this crane actually is going to be carrying a load, then it's going to have something we call the angular velocity, which is going to be the amount of the change of the angle that the crane is going to be moving at, but as a function of time. So how many radian per second we're going to have. Also, we're going to add some acceleration to do this movement, and in that case, it's going to be the angular acceleration, and we're going to consider it as a radian per second square. At the same time, the mass itself is going to have a linear velocity and linear acceleration, which is going to be how many meters we are going to move per second and how many meter per second square we are accelerating. So the parts and the components we have, and also the mechanisms, like the number of the components, the motion of one couples the motion to the others, and the synthesis of the mechanisms. Also the machine, like the mechanical systems, like the number of the mechanism we are going to have in one system. The statics static and dynamics of the mechanical system. Well, in the case of the static, we are going to have the system remaining static or moving in a very low speed. For the static, usually the sigma of the forces and the moment are going to be equal to 0. And also we can have a system in motion, which we call dynamics, where the sigma of the moments is not going to be equal to 0, but it's going to be the mass multiplied by the acceleration. Finally, for the analysis of dynamic system, we can consider the kinematics, which is study of the motion without considering the force. And we have the kinetics, which is going to be the study of the forces on the system in motion. So the best machinery we can have is going to be the human skeleton. So, learning objective for today's session is going to be first describe the fundamental of the rigid body dynamics and the motion analysis. Second, understand the implementation of the rigid body dynamics and the motion analysis in a product design and development process. Third, the understand of how to use the digital design tools such as the MATLAB, SolidWorks, Simulink, Simscape to conduct the rigid body dynamics and the motion analysis for the design analysis or the computer-aided engineering. So that's it for the introduction. Next part is going to be about rigid body dynamics. The rigid body dynamics, and we'll start with the fundamentals of the rigid body dynamics. So for the rigid body dynamics, we're going to start first with about the basic concepts of the dynamics. So dynamics include two aspects, as we mentioned earlier. The first two dynamics aspects are going to be the kinematics, which is study of the motion of the body without consideration of the force, which causes the motion. So we are going to ignore the force or the forces present in the system or the mechanism and only concentrate on the solving for the position, like the velocity and the acceleration. So sorry, position, velocity, and acceleration. The kinetics, which is dynamic force analysis, and is going to relate to the action of the force on the system or the mechanism to their resulting motion. So we are going to study a relation between the forces and the accelerations and introducing forces into a kinematic system. So the applications of the dynamics, the basic principle is to the analysis and design of the machines or the structures operated with a high speed and appreciable acceleration. The moving structure, like the robot devices, the rockets, the missiles, the spacecraft, the ground and the air transportation, the vehicles, the machinery of all the types, such as the turbines, the pumps, and extra. The fixed structures subject to shock or impact loads, like the gear trains, also going to be an application for the dynamics. Now, the general procedure for the dynamics analysis are: first, you need to identify the dynamic problems and try to correlate the actual physical situations with the theories studies. Second, you need to draw a necessary diagram and tabulate the problem data. Third, apply the relevant principles generally in a mathematical form. Fourth, solve for the necessary equations algebraically and as far as the practical by making sure that they are going to be dimensionally homogeneous and using the consistent set of units. Fifth, complete the solution numerically, and finally, study and review the answers with technical judgment and common sense to determine whether it's going to be seems reasonable or not. Okay, so by a simple comparison between the design analysis versus the static analysis, first we have to note that there is no loads are going to be applied to a structure are going to be truly static, since all the loads must be applied on structure in some of the particular sequences during the finite period of time. So the time variation of the force is inherently involved. So the question is, when do we optimize for dynamic analysis and when the force changes as a function of time? So when the nature of the force is going to be is such that the causes of the acceleration do a significant that the initial forces cannot be neglected in the analysis, we need to apply the dynamic analysis. Also, when the static analysis is going to be when the loading is going to be in such that the acceleration caused by it can be neglected. The same load may be treated on one structure to be a dynamic, whereas on the other can be a static. Now we come to the rigid body motion. So for a particle, is a physical object that we can consider its mass to be concentrated at one point. So just imagine that you're going to have a spherical metal ball. So it's in the center is going to have its all mass there, and then the weight. The particle is going to be a body of negligible dimension when the dimensions of the body are going to be irrelevant to the description of its motion. The body may be treated as a particle. There are, of course, no such objects, but assuming that the objects to be particles give a great simplification to in the description and often going to be without any significant loss of the accuracy. So for the rigid body, and this is more than the particle, is a rigid body can be considered as a combination of a large number of the particles in which all the particles will remain at a fixed distance from one another, both before and after the applying of the load. And the changes in the shape are going to be negligible compared to the overall dimensions of the body. No deformation should occur in the rigid body. Finally, we have dynamics of the planar mechanism or rigid bodies. This can be a planar kinematics, it can be a planar kinetics, where the forces and the acceleration should be included. We can have planar kinetics for the work and the energy, and we have a planar kinetics for the impulse and the momentum. So for the planar kinetics and the planar kinematics and the kinetics is going to be for a two-dimensional analysis only. So the planar kinematics of the rigid bodies, this can be a translation, this can be a rotation about a fixed axis, it's going to be relative motion analysis like the analysis for the position, for the velocity and the instantaneous center of the zero velocity, and for the acceleration. Also, the planar kinematics of the rigid bodies can be about the relative motion analysis using the rotating axes. So when all the particles in a rigid body move along the path that actually equidistant from the fixed plane, the body will said to be undergoing a planar motion. So you can see that we're always going to have the particles going to have the same distance between the paths, and thus going to be a planar motion. So there are three types of the rigid body planar motion. The first one is going to be translation. Translation in this type, the motion occurs if every line segment or the body will remain parallel to the original direction during the motion, like what we have in the upper diagram. Now we have another two, which a self translation can be a recliner translation. Occurs when the path of the motion of any two particles of the body are going to be along an equidistant straight lines. But the curvilinear translation occurs when the paths of the motion are going to be along a curves lines which are going to be an equidistant. So once again, that's what we can have in the rectilinear, and that's what we have in the curvilinear. So in addition to translation, we can have rotation about a fixed axis. Then that's happening when the rigid body rotates about a fixed axis. All the particles of the body, except those which are going to lie on the axis itself, are going to be moved along a circular path. So that's what happens once again. This is the body. It has multiple particles. Some of the particles are going to be along the line of the rotation. So they're not going to be rotating. But anything away from that by a certain radius is going to be considered to be having a rotation around a fixed axis. Now the last type is going to be the general plane motion, and that's when the body is going to be subjected to a general plane motion. It will undergo a combination of the translation and the rotation, and the translation occurs within the reference plane, and the rotation will occur about the axis perpendicular to the reference plane. So just imagine that you are going to throw an object in the air, it's going to make a rotation around itself, and is going to be felt. So we're going to have mix between the rotation and the translation, and that's what we call the general plane motion. So now we're going to have a reminder about the 3 Newton's law of laws of motion. So we start with the first law, saying that the particle is originally going to be at rest or moving in a straight line with a constant velocity. It will remain at this state provided that the particle is not going to be subject to an unbalanced force. So if you're going to put something on the table, it's not going to move unless we're going to add a force uh, to move it, to push it. If I'm going to throw something in the air, it will come down because there's another force will overcome the force I added to it, which is going to be the gravity force and the weight. The second law, which is the basis for most of the analysis in the dynamics, which is saying that the particle will act up on the unbalanced force F, will experience an acceleration A that has the same direction of the force and magnitude that directly proportional to the force. So when you actually again to push the particle is going to have acceleration at the same time, is going to have the same direction and the same magnitude proportional to that force. The higher force is, the higher acceleration is, and it's going to be in the same direction. The third law, which is the principle of action and reaction used in the statics, is say that the mutual force of action and reaction between the particles are going to be equal, opposite, and collinear. So we use the Newton's second law of motion, and we need to know first what is the law. So usually the Newton's second law of motion is about the general motion, says that the time rate of the change of the momentum of the body is going to be equal to the magnitude of the applied force and acts in the direction of the force. So we're going to have the two cases. In the case of the linear translational, we're going to have that the mass multiplied by the change in the velocity is going to give you the force. So the force is going to be equal to the mass multiplied by the acceleration, because the change in the velocity with the time we call it the acceleration. For the rotational case, we're going to use that the I multiplied by the d omega, or the change in the angular acceleration, divided by the change within the time, is going to give you the moment. Or the moment is going to be equal to the I multiplied by the alpha, where the alpha is going to be the angular acceleration. So here are the keywords. The m is the mass of the object, f is the force acting on the object, the v is the velocity of the object, the linear velocity of course, the a is linear acceleration of the object, t is the time, I is the mass moment of the inertia, and this will differ from a different section to another. The m is going to be the applied moment or torque, and the omega is going to be the angular velocity of the object, and the alpha is the angular acceleration of the object. So we have four basic quantities, which are going to be the force, the mass, the length, and the time, are not all independent from one another. In fact, they are related to a Newton's second law of motion. The meter, the second, and the kilogram are the base units. And all the units of the force are going to be derived units. Like, for example, is going to use the kilogram meter seconds to give you the Newton. And we have the unit measurement in the SI unit. For the length is going to be the meter, the time is going to be in seconds, the mass is going to be kilograms or kg, the force in Newton is going to be 1 kilogram meter over second square. Well, just try to remember that the meter over second square is the acceleration, the kg is the mass, so mass multiplied by the acceleration is going to give you the Newton. The easiest way to do the analysis for the motion is by using the position factor. So the position factor vector at the point is going to be defined as the r value, or the length of this vector, is going to be equal to its location in the x, y, and the z direction. So usually we denoted the x with the I, the y with the j, and the z with the k. Positive, they're going to be on the positive direction of the axis itself. So in this diagram, we can see that That's the x-axis in that direction. So if that point, the x displacement is going to be on the positive side, so I'm going to have positive xi. The same thing with the y and same thing with the z. So the magnitude of the r, or the length of that vector, is always going to be positive and always going to be defined as the under square root of the x square plus y square plus the z square. For the plane motion, well, we're going to have it in two directions. In that case, the z value is going to be equal to 0. The direction of the r is going to be specified up on the components of the units of the factor, which is going to be equal to the ur is equal to the r divided by the magnitude. So we need to divide this value by that value. And this will give me direction and the x, y, z for that vector. Now we can represent the velocity and the forces as a vector. So we start with the velocity vector. Velocity vector at the point, or the velocity change, the dimension change within the time. So we're going to have the velocity xi plus the velocity yj and velocity zk, which may again to be the same equation that we had for the vector itself divided by the time change. Okay, so that means that the Vx is going to be actually the x value divided by the time. Okay, so the Vx is the x dot, the Vy is y dot, and the Vz is z dot, or the change in the velocity in these axes. The velocity also has a magnitude, which is going to be defined by the same method, so it's going to be on the square root of the velocity to the x fraction square, plus the velocity to the y direction square, plus the velocity to the z direction square, all on the square root. And the direction of the velocity usually going to be specified by the components of the unit vector itself. So it's going to be once again the velocity vector divided by this magnitude, and the v always going to have always going to be tangent to the path. Also, the acceleration can be represented as a vector. So the acceleration vector at the point is going to be the change of the velocity with the time. And this will be making the vector of the velocity to be changed with the time to give it the acceleration in the x, y, and the z direction, where the ax is the change in the with the time for the velocity, or is going to be double dot or double change for the distance within the time. Same thing for the y, and the z. The acceleration also have a magnitude that can be defined as the magnitude of the multiple accelerations. The acceleration has a direction specified by the components of the unit under the vector, which is going to be of the unit vector, which is going to be the vector divided by its resultant. Since the alpha represents the time rate of the change velocity, the a will not going to be a tangent to the path. So for the translation of the rigid bodies, we can simply have a position vector at 2 points. For example, the location of the points A and the B, and well, I'm talking about the A and the B. Well, let me have the pen to show you that here. So that's the point A is here, and that's the point B is here. So the location of the point A and B in a rigid body are going to be defined from the fixed X and Y reference frame from its origin at O by using the position factor RA and the RB. So we're going to have the RA and the RB, we can have the vector RAB as what you can see here. So the next step is simply going to be that the translating of the x prime, y prime coordinate system is going to be fixed in the body and has its origin located at the A. Hereafter referred to us as the base joint. So the position of the B with respect of the A is going to be denoted by the relative position vector RAB, where the vector by vector addition we can have the value is that the RB is going to be equal to the RA plus the RB slash A, or the RB slash O is going to be equal to the RAO and equal to the RB slash A, or what we say is that the value for that link as a vector is going to be equal to this vector plus this vector. Okay, that's it. That's what we call the relative position vector. The same thing actually can be done for the velocity. So as we had for the distance, the same thing can be repeated for the velocities. So for the velocity vectors at the 2 points is going to be a relationship between the instantaneous velocity at A and B, which is going to be obtained by taking the time derivative of the position equation, which is going to yield simply with the velocity B vector is going to be equal to the velocity A vector plus the change of the length of the vector RBA within the time. So you remember that we said that that was the scenario we had. That's the R, this is the A, and this is the B. So this value is going to be a constant, so it's not going to be changed within the time, and this will tell me that this derivation is going to be equal to 0. So we can say simply that the term dRBA to the delta t is going to be equal to 0, and this will give me that the velocity at the B is going to be equal to the velocity at the A. Now the acceleration is going to have the same things, because once again, if we don't have velocity, we don't have acceleration, because the link AB change nothing within the time, and thus the acceleration at B is going to be acceleration at A. So it will indicate that all the points in the rigid body will subjected to either a rectilinear or curvilinear translation move with the same velocity and acceleration. Now we come to the rotation of the rigid bodies around the fixed axis. So when a rigid body is rotating about the fixed axis, any point located in this body will travel along a circular path. So we're going to take a look to this diagram. You can locate the point P. Actually, let me use the laser pen. So the point P is here. It's going to be away from the center O by distance R. So this point, when this body is rotating to the counterclockwise rotation, is going to travel in this red path, coming back to the same position multiple times. So what's changing here is not the distance, not meters, but it's going to be the theta to be changed. So we're going to have the angular acceleration and angular velocity, which is going to be change of the theta with the time, and this will be how many radian per second. And we have the angular acceleration, which is going to be the double derivation of the theta. So the angular motion, where the point or the particle is without dimension, and so it has no angular motion. Only the lines or the bodies undergoes the angular motion. So consider that the body shown and the angular motion of the radial line R are going to be located within the shaded plane and directed from the point O on the axis of the rotation to the point P. The angular position at the instant shown in the figure, the angular position of the R is going to be defined by the angle theta. So the change is going to be angular displacement in radian, measured between the fixed reference line and R. The angular displacement, where the change in the angular position, which can be measured as the differential of the delta theta, is called the angular displacement. So the time rate of the change in the angular position is called the angular velocity, or the omega. Since the delta theta occurs during the instant of time, or dt, then the omega is going to be the change in the angular displacement within the time of this change. And now the angular acceleration is going to be the alpha, which measures the time rate of the change of the angular velocity itself. And the magnitude of this vector may be written as the alpha is equal to the change of the omega with the change in time, or the double change of the angular displacement to the change of time square. So the line of action of alpha is the same as that for the omega. However, its sense of the direction is dependent on the whether the omega is going to be increasing or decreasing. So if it's going to be increasing, the alpha and the omega will be the same direction. If it's decreasing, it's going to be to the opposite direction. Or what we call the acceleration, that means it's increasing, or deceleration means it's going to be decreasing. So by eliminating these two equations, we obtain the differential rotation between the angular acceleration and the angular velocity and the angular displacement, or the alpha, the theta is going to be equal to the omega, the omega. Okay, so the change in the acceleration to the acceleration of time of displacement is going to be equal to the change in the velocity as a function of the velocity itself. So the constant angular acceleration, we can simply have the equation that the alpha is going to be the alpha constant. And in that case, the omega is going to be the omega O plus the alpha CT. And the theta is going to be the theta O plus the omega OT plus half of the alpha CT square. And the omega square is going to be equal to the omega of the origin point square plus 2 alpha C theta minus the theta O. So just if I'm going to explain this one, that means that the acceleration at any point, okay, is going to be equal to the initial acceleration, the velocity at any point is going to be equal to the initial velocity plus the alpha, which is the angular acceleration multiplied by the time. And for the theta, it's going to be the original theta plus the original omega t plus half of the acceleration t square. And finally, for the omega square, is going to be equal to the omega original square plus 2 alpha c theta minus theta O. Now, the direction of the v is going to be tangent to the circular path. So we said that we have the circular path r, that's the circular path r. The velocity is going to be perpendicular to it, 90 degree. The same thing for the acceleration, we're going to have the tangential acceleration, which is going to be the same direction of the velocity, and we have the normal one, which is going to go toward the center. So both magnitude can direction of the v can also be accounted for by using the cross products of the omega and the rp. Hereby, the rp is going to be directed from any points on the axis of the rotation to the point P. So the velocity is going to be equal to the omega multiplied by the length of the link rp. When we say that's going to be a cross product, that means this can be a vector, and the omega is rotating, as you can see here, around the z-axis. That the z-axis, the r is going to be a function of the x and the y, and thus we're going to have the cross multiplication of the vector, as you remember it. So the change of the dr to the dt is going to be equal to the velocity and equal to the omega cross the vector rp. For the acceleration of the p can be expressed in terms of its normal and tangential components. The tangential one is going to be a function of the acceleration. So tangential acceleration is going to be the tangential acceleration angular acceleration multiplied by the r. The normal linear acceleration is going to be equal to the linear velocity square multiplied by the r. It might be expressed in the terms of the vector cross products as following. So the acceleration is going to have two components. That's the first one, change in the velocity to the dt, which is going to be the angular acceleration multiplied by the rp, plus the omega, which is the angular velocity multiplied by the change of the link to the dt. Or we can write it down like that. We're going to have sets of I and j's, and then we're going to find the magnitude of it by the normal methods. So the acceleration is going to be tangential plus the normal, and it's going to be the alpha cross r minus the omega square r. Now this is a scalar and this is vector, and we're going to explain that more closely in the class. Now for the relative motion of the rigid bodies in general. So if the velocity of the length BA has a magnitude of the VBA, which is equal to the omega multiplied by the RBA, and the direction which is going to be perpendicular to the length of the RBA, then simply we can say that the V point B is equal to the VA plus VB over A. And thus, that's what we call the relative velocity equation. So the relative velocity VB represents the effects of the circular motion about the point A. It can be expressed by the cross product equation, or the VBA is going to be equal to the omega multiplied by the length of the link RB to A, and the VB is going to be equal to the velocity at the point A plus the omega cross the RBA. We're going to have an example for that later, and I will try to simplify it for you as much as I can. So we come to the first example. It's about a cord that wrapped around the wheel, which is initially at rest. When we say initially at rest, that means the angular velocity now, it's 0. And the alpha, of course, is going to be 0 as well. If a force is going to be applied to the cord and it's going to give the acceleration A is equal to 4t meter per second square, where t is going to be in seconds. So now this length here is going to have the acceleration of 4t meter per second square. So let's see what's happened. The omega now is 0, and we have the acceleration, which is a tangential acceleration, or the alpha r is given as 4t. So bear in mind, what will be the function as a function of time? What will be the angular velocity of the wheel? And what will be the angular position of the line of the OP in radian? So now what we need to do is we're going to use the only thing that we know, which is that the omega 1 is 0, and the A, or the acceleration of that link, is 4t meter per second. So the angular velocity, that's what we need, the omega 2. Okay, so we will start from the point by first analyze the problem. So what we have is the wheel is subjected to rotation about a fixed axis passing through the point O. Thus, the point B of the wheel at the circumference is going to have a motion about the circular path. And the acceleration of this point has both the tangential and the normal components. The tangential component is the APT, which is 4t meter per second square. Since the cord is going to be wrapped around the wheel and move tangent to it. As the angular acceleration of the wheel is alpha, and we can rearrange this equation that the APT is actually equal to the alpha multiplied by the r. And thus we can write down that the 4t that's been already given is equal to the alpha multiplied by the radius, which is 0.2. Now the alpha can be solved to be equal to 20 t radian per second square. And this will go to the clockwise direction. So hence we can simply say that the acceleration, that should be mentioned earlier, but yeah, that's the equation we're going to use, that the tangential acceleration mainly is going to be equal to the alpha multiplied by the r, and that's what we substitute actually in the equation 1. Now using the results, the wheel angular velocity omega can be now determined from the alpha, which is equal to the change of the omega to the change of time. So I think that you understand. What we're going to do next is we're going to do the integration for this equation. So we come to the point and we said that the alpha is equal to the dw, or change in the omega, to the time, which is equal to 20t. We can simply do the integration for both sides and find the value for the omega. Omega 1 is 0 because we're starting from the rest. Time 1 is 0. Time 2 is, I don't know how much it's good. No, we can find it as a function of time. So we're going to do the integration from both sides, and we're going to end up that the omega is equal to 10t squared radian per second. And the direction is going to be to the clockwise. Now further, the angular position theta of the OP can be found from the omega, which is equal to d theta to dt. So we're going to do the same thing now. The omega dt is going to be integrated to find the value of the theta. So we can write down the equation, okay, rearrange it, integrated. So we'll find out that the theta is going to be equal to 10 t up to power 3 divided by 3. Or is going to be equal to 3.33 t up to power 3 radian. That's it. That's the question. Okay, now once again, I'm going to repeat that on the whiteboard during the lecture time, again, to actually make you understand what we're doing here. Now, the other example on the relative motion. Now, the cylinder is rolls without slipping on the surface of the conveyor belt, which moving at 2 meters per second. The cylinder has a clockwise angular velocity, omega, which is equal to 15 radian per second at this instant. Determine what will be the velocity at the point A. So just remember once again that we having non-slipping. That means we're going to have the velocity at A can be found simply by making the rotation around the point B. So we need to sketch a line from B to A. That will be my link. And that link multiplied by that distance will give me the velocity at the A. So we are going to work with this solution. So solution for the vector analysis first. So you can see that this will be the link. Okay, that will be the velocity A, which is perpendicular to this line. So let me use the pen. I like to use the pen more than the highlighter. So the angle here should be 90 degrees. I know it's not made to scale. So now if I get to sketch here, this will be 0.5 meters because this is radius, and this is another 0.5 meters, so I can find the length AB directly, which is going to be the 0.5 square plus 0.5 square under square root. Now when I'm going to find the RAB, I know the omega, and then I can simply find what will be the velocity at the point A. By finding the velocity at the point A, I can find what will be the velocity at the point B. It's not going to be only 2 meters per second, but it's going to have two velocities, and we can find that by doing the what we call the relative velocity equation. So first we did the kinematic diagram, and since no slipping occurs, the point B on the cylinder has the same velocity as the conveyor. The angular velocity of the cylinder is known, so we can simply apply the velocity equation to B and the base point A as a base point, and the A to determine the value for the VA. So we're using the velocity equation that says that the VA is equal to the VB plus the omega multiplied by the RAB. Now this known now is as 2 meters per second. And the omega is given as 15 radian per second. We have to worry about the direction because different directions for the velocities. Anyway, the RAB has been calculated. As we mentioned, we have the 0.5 here, and we have another 0.5 horizontally. Okay, and then we can simply find what will be the value for the velocity A. So everything we have is available. So even if we're going to do it as a vector, what we're going to say that, of course, that's 5, 5. That means the angle here is, sorry, it shouldn't be like that. The angle is 45 degree. The angle here is 45 degree. This is 45 degree. And this will give me that this is 45 degree. And this one is also 45 degree. So the theta is 45 degree. And that's what we're going to discover by the solution. Anyway, so let's go with the calculation. The RAB is equal to 0.5 minus 0.5 for the I and 0.5 for the J. And we'll get to multiply by the omega, which is omega K, because it's rotating around the z-axis. So we put all the parameters for the equation down there. The VAI plus the VAY. J, and this will be equal to 2I, because that's the velocity we have at the point B. It's only have the x component positive, so it's going to be 2I. The omega is to the clockwise direction, and thus it's going to have negative value, so minus 15k, because it's around the z-axis. And we said that the RAB as a vector is going to be negative 0.5I, because it's going to the negative direction of the x-axis, and while the y is going to be 0.5j, because it's going upward. Now we have this one in, and then we can apply the multiplication process for the vectors. So we have here minus 15k times minus 0.5i. K times I is j. Minus and minus, we're going to have positive. So we're going to have 15 times 0.5j. The minus 15k times 0.5j, the k times j is negative I. So we're going to have negative times negative, and this will be positive value for the I component as well. So we can write it down like that. And then we can simply solve for the i's together and for the j's together. So you will find the velocity at the point A to be equal to 9.5 in the x direction and 7.5 to the y direction. Okay, so we just add for the x direction 9.5 meter per second, and y direction is going to be 7.5 meter per second. And thus I can simply find its magnitude and the value for the theta. Sorry, this one is hidden behind the photo. I'm going to move the photo later. Now, if we're going to do the scalar analysis, it's not going to be much different. I write down the velocity equation first, the relative velocity equation. Then I can say that the VAX is going to be the VBX plus the VBAX. The VAY is going to be the VBY plus the VBABY. And the VB is 2 meters per second. The VBY in the y direction is 0. And the VAB is going to be equal to the omega AB multiplied by the RAB. And we know that the omega AB is 15 meters per second. And the length of the link AB is under square root of the 0.5 square plus 0.5 square. Okay, and thus we're going to have that the answer to be equal to 7.5 multiplied by under square root of 2 meter per second. So we found the magnitude of that velocity. Now the theta we said is going to be 45, and we found that from the analysis. Okay, and you will tell me why during the class, because I mentioned that earlier. So now I can find the VAB to the x and VAB to the y by multiplying by the cosine of 45 and the sine of 45, and then we're going to find them both to be 7.5 meters per second, and I can find the magnitude and the x and the y. Okay, so yep, we just solved for that. I think that should be okay. So the same results has been obtained by using the scalar analysis. Now we finished with the rigid body analysis. Now let's go, so fundamental of the RBD. Now we're going to dynamic analysis of the system. So dynamic system analysis, um, well, you know that we're always going to have a time-varying nature of the excitation applied, which is the applied loads, and the response, which is resulting in displacement of the internal forces, stresses, strain, and extra. A dynamic problem does not have the single solution, but is going to have a succession of the solutions corresponding to the all times of the interest in the response history. A dynamic analysis is going to be more complex and computability intensive than the static analysis. So the inertial force, or the I value, will be generated when loading dynamically applied. The inertia is a property of the matter by which it remains at rest or in motion at constant speed along the straight line so long as it's not going to be acted by an external force. So just imagine something. If you're going to throw to your colleague a heavy bag or an empty bag, so you will find the empty bag is going to have less forces. The heavy bag is going to be heavier forces because of the inertia. The translation motion is a measurement of the inertia. Uh, the measurement of the inertia is going to be the mass. The higher the mass is, the higher the inertia is. For the rotational motion, the measurement of the inertia is going to be the mass moment of the inertia, or the I value. So the dynamic analysis procedure will start first with identification of the physical problem or the existing structure. So we need to identifying and describing the physical structure or structure components and the source of the dynamic loading. Second, we need to have a definition of the mechanical model or the analytical model. So it's a set of simplifying assumptions like the loadings, the boundaries, the boundary condition, and extra. Also, we have to have a set of drawings depicting the and adopted analytical model. Also, we have to provide a list of design data like the geometry, the material properties, and extra. We need to set the definition of the mathematical model, well, set of the equations, where the unknowns are going to be response sought, and then solve the model to determine the dynamic behavior. So start with a degree of freedom dynamic system like the one we have here. So you can see that we're only going to have one motion to be appeared, which is going to be upward and downward. So there are three key components of the discrete system. First, that the mass of the inertial element. Second, the spring element. And third is going to be the damping element. So that's the spring, that's the damping, and that's the inertia going to be equal to the mass. So structural dynamics modeling by relating the force inputs and displacement acceleration outputs. So the dynamic system in general includes the means of storing the potential energy, like the spring or elasticity, and the means for the storing, for storing the kinetic energy, like the mass or inertia, and the means by which the energy is going to be gradually lost, like the damper. The system involves the transfer of its potential energy to a kinetic energy and kinetic energy to potential energy, alternately, or simply the interplay between the potential energy and the kinetic energy. If it's damped, some of the energy is going to be dissipated in each cycle of vibration and must be replaced by an external source if a state of the steady vibration is to be maintained. The single degree of freedom spring mass system is subjected to a time-dependent force F as a function of t and have degree of freedom x as a function of t. So single degrees of freedom system, for example, can be the bars, the trusses, the beams, and the frames. The dynamic of the simple spring mass system is given by the equation of the mass multiplied by the x plus the k multiplied by the x to be as a function of t for the force. The above equation is a second-order linear differential equation whose solution for the displacement consists of a homogeneous solution and a particular solution. The homogeneous solution is the solution obtained when the right-hand side is going to be set equal to 0. A number of the useful concepts regarding the vibrations are available when considering the free vibration of the mass, that is when the force is going to be equal to 0, to be given by the equation that the mass, that the kinetic energy of the mass plus the one for the spring is going to be equal to 0. And then the omega square is going to be equal to the k divided by the m, or the spring constant divided by the mass, and thus we can rewrite down the equation in a new format. Omega is the natural circular frequency of the free vibration of the mass. The motion described by the homogeneous equation of motion is called the simple harmonic motion. A typical displacement to time curve is shown below. So it will look like a sine wave, okay, where the xm here, that value is going to denote for the maximum displacement or amplitude of the vibration. The tau, okay, the tau from peak to peak is the period of the vibration, and the omega is going to represent the circular frequency. So the other type is going to be the multiple degrees of freedom. We're going to have continuous structures approximated by this number of the degrees of freedom. The majority of methods and applications, linear and the time invariant models are going to be assumed. So for the multiple degrees of freedom dynamic system, the model analysis will be related to the eigenvalue analysis, where we're going to have two equations. One is going to be about the time domain equation, and the other one is going to be about the Laplace domain equation. So the eigenvalue analysis is going to be system poles and eigenvectors. For the system poles, we're going to have the resonance frequency and the damping value, and given by the following equation. The eigenvector is a model shape, transformation factor to a model space. So the motion analysis can be done by using the SolidWorks, and that's what we're going to cover in the next section. So we're going to introduce you briefly about the motion analysis using the SolidWorks, and also I think that you're doing, for the student who are doing the mechanical design, you're doing the same thing at the same time, and we can use the same examples. So we start with the SolidWorks motion. It is a CAD tool that supports the engineers to analyze and design mechanisms. It supports users to create virtual mechanisms that answer general questions in the product design. Like for example, what will the components of the mechanisms collide or interfere in operation? And will the components in the mechanism you are designing move according to your intent? And how much torque or force does it going to take to drive a mechanism, and how fast will the components move? Finally, what is the reaction force or torque generated at a connection, also called the joint or constraint, between the components or the bodies during the motion? So, for example, we can design for a single piston engine, and we will connecting the rod collides with the inner surface of the piston or the inner surface of the engine case during the operation. Will the piston stay entirely in the piston sleeve, And will the system will lock up when the firing force aligned vertically with the connecting rod? What will be the minimum firing load to move the piston? And what is the linear velocity of the piston? And what is the reaction force at the joint between the connecting rod and the piston pin? All these questions can be answered if we can use the SolidWorks for the analysis for the motion. General mechanism we can have, like the open loop system or the closed loop mechanism, can also be analyzed. So once again, we continue with the example of the dynamic analysis of the engine motion model. We're going to put the input in this example to be the omega value, and we can see that in the kinematic analysis, and the output is going to be the slider motion. In the kinetic analysis, the output is going to be resulting motion omega at the crank, because the input was the driving load P on the piston. So the general procedure for the dynamic analysis using the SolidWorks, first by doing the motion model generation, and this can be done by the motion mate, assembly mate, the drivers, which is going to be the motor, the load, which is going to be springs, for example, the damper and extra, the initial conditions, and the friction or the contact. Also, we're going to apply the motion analysis to get the result visualization or the post-processing, like the animation, the graph, the query, the report, and the AVI. We have three study options in that case, which are going to be the animation, which animate the simple operation of the assembly, the basic motion to support the effects of the motors, the springs, the collisions, and the gravity of the assemblies, and the motion analysis, which must be ticked as in the at ends. So to provide an accurate simulation and the analysis on the effects of the motion intensities, including the forces, the springs, the dampers, and the frictions on the assembly. So you can see that what we can do is start and make a new study, select what the type of the study. We're going to have multiple selections, like the calculate, the play from the start, the stop. We have the animation control, like the slider, which is going to decide what will be the playback speed we're going to have. We have the animation wizards, we have the simulation elements, and we have the event-based motion view. So we have two types of the rigid bodies defined by the SolidWorks, which is going to be the ground parts or the ground bodies, and this to be fixed reference in the space. Usually is going to be stationary. Also, we're going to have moving parts on the moving bodies to represent the single rigid components or the link that move relatively to the other parts or bodies. The unconstrained moving rigid body in the space has a 6 degrees of freedom, 3 translational and 3 rotational, while the ground body has none. So the constraint and the degrees of freedom in the SolidWorks are: first, the unconstrained rigid body in this space has 6 degrees of freedom, 3 translational and 3 rotational. When the joint or the constraint between the two rigid bodies is going to be added, degrees of freedom between the term are going to be removed. Like the joints, the assembly mates also going to be remove the degrees of freedom between the parts. Each independent movement permitted by the constraint, either a joint or an assembly mate, is going to be a free degree of freedom, which can be translational or rotational along the 3 perpendicular axes, either global or local. In creating the motion model, instead of completing the fixing of all the body motion, a certain degrees of freedom, which can be once again translational or and rotational, are going to be left to allow the designated movement as degree of freedom. The degree of freedom counts in the SolidWorks are: first, for the regular equation, the d is going to be equal to 6m minus n minus o, where the D is going to be the Greville counts representing the number of the free degrees of freedom mechanism of the mechanism. The M is going to be number of the bodies excluding the ground body. The N is going to be number of the degrees of freedom restricted by all the mates. And the O is going to be number of the motion drivers, like for example the motor defined by the system. For the kinetic analysis, the Greville count must be equal to or less than 0, and after adding the motors, otherwise the animation will not going to be run and an error message will pop up. The EDAMS solver recognizes and deactivates the redundant constraints during the analysis. Now, the last part of the session today is going to be about the motion analysis using the MATLAB Simulink and the Simscape. And this will be actually what we're going to do in the lab over the next 2 to 3 weeks. So the motion analysis using the MATLAB Simulink and the Simscape, the Simulink basics is going to be covered, the ordinary differential equations as a block diagrams, and the navigating of the Simulink models. The case study 1 is going to be one link pendulum. The case study 2 is going to be slide by cranks mechanism, and case study number 3 is going to be the 4-by mechanisms. And actually, if you try to check the Brad Horton tutorial about that, it will give you many hints about the system. So the self-based courses also available on the MATLAB, like the MATLAB on RAMP, the Simulink on RAMP, we have the Simscape on RAMP, and we have the Simulink fundamentals. Each one is going to have a different models. You can see that the course can be anything between 2 hours up to 8 hours for the Simulink fundamentals, but we'll try to keep you actually within the limits of how to use the model we're going to give you first, then we're going to go for a further advance in the future. So once again, we covered all the topics for this week, and for next week we're going to talk about the rigid bodies dynamics or the single degrees of freedom system. And that's it for this week, and thank you very much for listening, and see you soon.